Alright guys, let's continue. So 41. Okay. So standard reduction potential for reduction of permanganate to manganese. So that's this to that. Okay. So this is a simple application of the Nernst equation, right? E equals E standard minus RT ln Q all over NF. So 1.51 minus 8.314 over times 298 over 5 times 96,500 times ln of Q. Well, how do you figure out ln of Q? Well, Q is 0.02. Right, everything's balanced. Check that first, but it is over 0.01 times 0.2 to the 8th power. Perfect. So plug this into your calculator. You're going to get B. Right, just checking. Yeah. All right, perfect. All right. So now 42. Okay, 42. So for this question, you're gonna have to know something that's really, really commonly tested. It's that delta G is not a state function. You can't just add them up. You have to weight it. Weigh it, right? So here's what I mean. There's a formula. Ne N1E1 plus N2E2 plus N3E3 equals N4E4. N4 equals presumably all of them, the sum of all of them, as we have here, right? Let's take a look at these. Look at these electrons adding up. Look at these protons adding up. Stuff cancels out. These cancel out. Yeah, exactly, right? So how do we figure this out? Well, just add them up. You're going to get 1.78 and divide it by 4. By 8, by 9. 8, sorry. Okay, oh my god. So 1.78 over 8. Does this look like an answer? 0.22? No. This is the trap that they want you to go through. So you're going to have to go individually and multiply these things out. So 1.15 times 2 plus 0.74 times 4 minus 0.11 times 2. Okay. So we get 5.04. Now, we're going to divide this by 9. 1 second. 2 times 1.15. 4 times 0.74 minus 0.11 times 2 divided by 8, sorry. So you get 0.63. Alright, perfect. So B. Alright. Next. This is about intuition. That's it. You're going to have a bigger jump. I think it's proportionally, but it could be additively as well. Like if you see this is 6,000 and this is 3,000 and this over this is way less than this over this. This is about 6, 5, and this is not even greater than 1. So this is a big jump. So this electron has to be in a lower energy level. So this has to be group 2 because these two electrons are normal. You go to a lower group, it's closer to the nucleus, higher electrostatic forces. So yeah. Alright, let's move on to the next batch of questions. Okay. So, alright. So this is gonna get more conceptual, right? In a ground state gas phase, I believe this is some atom. Okay. SB atom, how many electrons have the quantum? Okay. Okay. So SB, right? If you look at the periodic table, right? SB is next to 10, right? So it's going to have a configuration of, right? If you do the configuration correctly, 5s2, 4010 stops here, 5p3. Okay. So what is this question even asking? Well, we know 5s2, 4010, 5p3. N equals 5, L equals 1, so P, this is P, and ML equals 0, so it's Y, right? Because -1 is X, 0 equals Y, and 1 equals Z. Perfect. So there's 3p electrons, one of them is going to be in Y, so the answer is 1. Alright, nice. Alright, we are about to be 3/4 through the test. Okay, 45. Two atomic orbitals have the same number of radial nodes. Alright, formula for that as well, n minus L minus 1. Same magnetic number, quantum number. Okay, so this is the -1, 0, 1 I was talking about for p orbitals. For s it's 0, for d it's -2, -1, 0, 1, 2, and all that, right? Okay, principal quantum number n. It's not the numbers that matter, it's the difference that matters. So, yeah. You can have 5 and 3, you can have 4 and 2, so this is neither. Alright, the p block elements in the third row of the periodic table. Let me clear some stuff up real quickly. Okay. This is a nice question. So if you look at the periodic table, you're gonna see that congeners is just corresponding group elements. So O and S are congeners or congeners. These are congeners. All of these are congeners of each other. Just elements in the same group are congeners. They have similar properties. Nice. So what does this tell us? Right? What is this gonna tell us? So it's basically saying that these elements have higher electron affinities than these elements, which is true because Cl- has a higher electron affinity than F-. Now here's the reason why. So this is because period 2 elements, n equals, otherwise known as n equals 2 elements, and n equals 3 elements. These are going to have, the n equals 3 elements will have p orbitals much higher in energy than s orbitals. But for n equals 2, p orbitals are similar energy. Right? Okay, so what does this tell us? When you're adding an electron, you're going to get electron-electron repulsion. However, p orbitals are 2p orbitals are smaller than 3p. So that E minus repulsion in 2p orbitals will be pronounced much more than in 3p orbitals. So it's going to be less favorable to add it to F than Cl. Yeah, perfect. So the heavy elements have more protons, but they're bigger, so that cancels out because atomic radius. So no, this isn't. Yeah, no. Okay. Yeah, that's just not true. Sure, but there's other factors that need to be taken into account. Um, Heavier elements have more blah blah blah. Okay, more nodes. What are you talking about? Really? Like, no. Yeah, lower energy, more stability, more favorable, but it has nothing to do with that. So let's see. All right, so elements are closest in electronegativity. So all right, CAL, OCL, NP, PAS. All right, I think I memorized those. All right, let's see. CAL, NP, OCL, PAS. All right, all right. So more protons and smaller. This is a recipe for an increase. No. And P, this is a recipe for a... Actually, wait. You're increasing the number of protons, but the size is increasing, so it's gonna decrease. Sure, there's more protons, but they're gonna be... I don't think they're gonna be too far apart. O and Cl increase because more protons, and a decrease due to the charge. But this decrease, sorry, not charge, size. This decrease due to size is going to be greater than this increase. So it's still going to decrease. Now, N to P is going to decrease. Um, Now, what are you left is? P and AS. Okay. Look at this insane amount of elements here. This is good for us because what's going to happen is the proton increase balances with its charge, with the size decrease, my bad. So they're going to be really close. And in fact, I believe they're like 1 point off the Pauling scale, like 1 decimal point off, like 0.01 or something. I don't know. I'm not 100% sure. But yeah, PNAS, because there's so many atoms, there's going to be a size decrease that matches up with the proton increase. So it's going to be PNAS. All right. All right. Alpha decay, beta decay, positron emission, spontaneous fission. Okay. So the method is elements with high amounts of neutrons to protons undergo beta, but it's not really asked as much for alpha decay. Like alpha decay is mainly those radioactive elements that are after bismuth, right? So polonium, astatine, like you have all of these radioactive stuff, right? So what's it gonna be? Well, let's see, 212 polonium, it's higher, but it doesn't matter. It's gonna go alpha decay. Alpha decay is going to be the answer. Because if it's either alpha decay or beta decay and it's super unstable, it's gonna go to alpha decay because that's the main method. Which species has a square planar geometry? So let me just write this for you. After bismuth, alpha decay. Perfect. Which species has a square planar geometry? Okay, this is about something called crystal field theory. Well, at least this is how I solved it. D8 complexes are square planar. So let's look at what's going on here. Right? BH4 minus, nah, it's tetrahedral at best. Right? S4, SF4, you're gonna have, I believe, a lone pair. It's gonna be trigonal. No. Trigonal bipyramidal, maybe? I think so. Because if you draw, you're gonna have 5 electron domains. Yeah. Okay. Um. Yeah. It's a common. I think it's commonly asked. SF4. Okay. ZnCl4. Okay. This is where we get into crystal field theory. So if you look at the periodic table, right, you're gonna see some things. You're gonna see that for transition metals, when you're in that D block, right? Let's look at zinc. Zinc is D10. AU. It looks to be, right? It looks to be D9, but is it? Is it really? Don't forget this massive block of elements here, right? So let's really take this apart. The actual configuration for gold is going to be let's figure this out together, So gold, I have my printed table here, but you're going to see that it's off from xenon. So xenon is the closest noble gas. There's a way to do this. It's 1s, 2s, 2p, 3s, 3p, 3d10, sorry, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6x, 6s, 6p, 6d, 6f, right? So what's going on? Well, we're gonna have to match this, right? Cross, cross, cross. 1s2, 2s2, 2p6, 3s2, 3p 3p6, 4s2, 3d10, 4p. It's like an order, right? This way, this way, this way. This is how you figure out electron configurations. It's kind of complicated, but it's easy to understand though once you get it. So you just keep going. So 3d10, 4p. So if you think about it, right? Gold's electron configuration, you're gonna have Xe in pseudo-noble gas configuration, and you're gonna add 25 electrons, right? So it's gonna be Xe. Yeah, this is not my thing. All right, Xe, and it's gonna be, well, Xe is 5p, right? So you're gonna go 6s2, 4010, 5p6. No, my fault. 6s2, 4f, 4f14. So we have 9, right? So 9e minus left. So 49. Perfect. It matches up. So this is the theory behind electron configuration. You can look here because of the way it's arranged. It looks like it's 9, right? But is it though? Is it really? Because 49 is not what we want. Okay? If you think about it, the gold's electron configuration, it actually reduces to D8. And there's a reason, right? Because you have your 6s2 here, 4f, 5d, 6p, and then you have your 7s, right? So basically what's going on here, you have to look at its charge. Here, gold is Au3 plus. Au3 plus, right? So you're gonna have to remove 3 electrons. Now which will it be? 2 here first and 1 here. So you're actually gonna end up with 4f14, 4d8. Sorry, 5d8. Yeah. There you go. Highest. Next highest, and you don't have enough to remove from 4f. So you're gonna have a d8, and that is going to be square planar. Zn, on the other hand, is d10, and here it is plus 2, so it's gonna stay d10, but with its s2 electrons removed. Okay, so yeah, crazy. All right, which isomer of CNO minus is most stable? Cool question. Let's figure this out. You have to do this with formal charges, unfortunately. Okay, but it's not too hard. Draw it out. C double bonded to N, which is single bonded to O. N double bonded to C, which is single bonded to O. CON has two forms. C double bonded to O, double bonded to N, or C triple bonded to O and single bonded to N. The second is a major resonance contributor, It is more stable formally if you figure out all the charges. So when you do your formal charges, you're going to notice that CNO is more stable. Why? Because not CNO, NCO. Because first one, CNO has a negative charge on carbon because there's a lone pair. So that's you can rule that out almost immediately. Sure, we have a plus charge on nitrogen, negative one charge on oxygen, but carbon, no. NCO has a zero on C, which is always good. Negative one on O, and a zero on N. Seems really good. And then C double to O double to N is just terrible. It's just terrible. It's just outright bad. You're gonna have a mess, right? Carbon's gonna have lone pairs. It's just weird, but it works. It works by the Lewis structure. I believe there's a lone pair on the carbon and two lone pairs on the nitrogen. Okay, but it's not what you want, right? Now, C triple bonded to O and single bonded to N. I believe you're gonna have zero on the N, zero. No. Yeah, zero on the O, and a negative one on the carbon. But still, with all this stuff going on, you're gonna have NCO as your best option, right? And cyclic, you got three atoms. You literally have a triple bond, and you're trying to make a cyclic structure. That's just gonna be messed up. You're gonna have, at best, this is what you're gonna get: tons of angular torsion. How are you gonna even make this bond? It's just gonna be a mess. It's terrible. So NCO, linear NCO minus. So recap, this is all based on formal charges. A is right out bad, you have a lone pair on the carbon. D is terrible, so C. And B, you look through the formal charges, you have a major resonance on C, triple bonded to O, and bonded to N, but it doesn't really work best with O as a center atom. And of course, carbon isn't ideal with its lone pairs. But yeah, pretty much that's it. Okay, so now that's the 50th question. All right, see you in the next video.